Hi everybody, this video will have some practice questions on basic usage of tangents in physics. For the following graph, or this is the same graph drawn many different times because we have different parts to the question, assume that all numbers are good to two significant figures or two significant digits. We can do that. We're asked to first calculate. So the command term calculate means that we need to show all of our work and come up with an accurate answer. The average rate of change, so average rate of change in this case of position here is plotted in the y-axis with respect to time, being this axis over here labeled as time. So sometimes we might not see it say with respect to time, and if that happens in physics, sometimes we can just assume that it's with respect to time. So in this case, we want the average rate of change, and in order to find the average rate of change, we need to find the slope between 2 points, so we need 2 time periods. Here we are given the 2 time periods for all the cases. So for first part of part A, we're asked to find it for 0 to 4 seconds. So the average rate of change here will equal, okay, with respect to time is equal to the slope between 2 points. So the first kind of mark here is given based on the recognition of this idea. So then the slope is going to equal to rise over run, or delta y, or change in y over change in x. So between times 0 and 4, this is times 0, and this is time 4. So we can see that in the first one, my time is 0, my position is at 3, and for the next one, my time is at 4, and my position is at 3, and I want to find the slope of this line. Right away, you can see it's flat, it's 0. So you can write that when that's the case. You don't have to do all the calculation, but here I will write delta y, 3 minus 3, 4 minus 0, which is equal to 0. And my units for this is meters per second. So the average rate of change for between times 0 to 4 here will be 0 meters per second. That's part I. For the second part, the idea is the same, so I'm going to leave this part the same. And the slope here again is delta y over delta x. So we're looking in between time 4 and time 6. So time 6 is here. So we're trying to find this slope over here. We already have this point. This point has a time of 6 and position of 4. So to find the slope, we're going to subtract 4 by 3. And we're going to divide that by 6 minus 4. So that's the change in y, so 4 minus 3 is how much y or our position has changed, and 6 minus 4 represent how much our time has changed. So once I have that, I'm going to get 1 over 2, or in this case 0.50, because two significant figures. With a 0, you don't have to show the number of significant figures if it's just 0, but for all other values, please do, and this will have a unit of meters per second as well. Finally, for part 3, it's the same idea. So we still need to find the slope because it's still the average rate of change. And this time is between 6 to 10 seconds. So 10 seconds we're here. So I'm going to draw my line. We're going to find the slope. We know already that slope is negative because it's slanted downwards. And in this case, this point over here has a time value of 10 and position value of -2. I'm going to put those values in. And now my slope is going to be change in y over change in x. So my change in y is -2 minus 4, and my change in x is 10 minus 6. And when I do that, I get -6 divided by 4, which is equal to -1.5 to two significant figures, meters per second. And again, you can also write it as -1.5 meters per second squared, or meters second to the -1. So these are my average rate of change for between these periods, so that those answer the first question. In terms of necessary steps to these questions, somehow you need to relate the average rate of change with the slope, and you need to be clear on that. If you just write slope is equal to this, it doesn't really answer the question, unless later on here, after finding it, you're going to say that the average rate of change was this slope, therefore the average rate of change is 0 meters per second. So that link needs to be there. Finding the slope needs to be there with showing clearly some of the points. So by doing the subtraction here, we'll know that you have used the points, but it will be nice to show the points in the graph as well. And you need a final answer with proper units as well for these types of questions. For part B of the question, we're asked to sketch the tangents at 1 second, 10 seconds, and 13 seconds. So let's do that. I'm going to start off, let's use purple for part A. So 1 second, and then we got 10 seconds, and I'll use red for this. So 1 second is approximal, it's exactly here. And if I want a tangent to that, I have to draw a line that kind of represents that slope as best as possible. So that wasn't very good. Let's try that again. Sometimes it takes a few times, and as you keep doing it, you just get better and better at it as well. And again, you can see this, even this one, a lot of spacing here, too much spacing here and not as much there. So I'm going to try it again and shift it a little bit. And this one is pretty good, I think. I like this one, so I'm going to keep it there. And you can see that I'm trying to draw a very straight line using my hand, so it's a little bit more challenging. That's why if you have a ruler, it works better. With this app, I can't use a ruler, so that's why I'm doing it free-handed. So I got my first one. I tried to draw a big, long line because later on I will need to use the tangent in the second part of the question to calculate the slope. And when we're doing that, we don't want to have 2 points too close to each other. We want to try to pick points that are far from each other. So try to use all of your graph when you're drawing your tangents. At the next one is at 10 seconds. I said I'm gonna use pink for that, so let's do that. So at 10 seconds, our pointer is over here. We can see that our slope is so imagine you're a person walking on this line. It's really easy. There's no slope over here. So you walk straight, and then you start to the slope is gonna start increasing and increasing and get steeper and steeper in the negative direction. You're gonna go in this direction. It's very, very steep around here. And then the steepness starts to taper a little bit. It'll get less and less and less and less and less steep. And at this point over here, right at about this point, there is no steepness. The steepness right here is actually 0. And then it starts to get very steep and positive this time. So it's easy to come down here because you're moving downwards, but as you try to go up, it gets more challenging. So right here, and once you do calculus, this becomes a lot easier. Um, you will have to represent this using one line. It's just a straight line. And yeah, that's it. So that's the tangent at this point. And again, you can see if I were to draw a tangent here, it would be something like this. Here it would be something like this. Here it would be something like this. Here it would be something like this. And right here, straight, and then it starts to increase after. Okay, finally, my last one is at 13 seconds. So 13 is right here. Pretty much I have a straight line at this point, and a tangent to a straight line is just that straight line. So this is also going to be a horizontal line in this direction, and that's my tangent, the red for 13 seconds. So write them down too. So this is 13 seconds. So especially if you're doing this using the same color, make sure that they labeled. So this is tangent. The first one is 1 second, and the pink one over here is 10 seconds. Now, where it says hence, this command term means that you want to use the information from previous parts of the question. It could be the first part, it could be the second part, but one of the question. Use those information to estimate the instantaneous rate of change of position with respect to time. So when we're talking about instantaneous rate of change, we always have to use the slope of a tangent. So this is kind of saying slope of a tangent. Position with respect to time. So position is in the y-axis. So that's going to be the change in position is going to be on our y-axis, and with respect to time, that's going to be on our x-axis. So the slope delta y over delta x, or change in position over change in time. I'm going to do some shifting here, and all I need now is the tangents. And to find the instantaneous rate of change, in this case of position with respect to time, I have to use slope of the tangent. So the idea needs to be there, and you need to mention that the instantaneous rate of change can be found by this slope. And then you can just go ahead and find the slope. So for 1 second, the slope is delta y over delta x. And what's delta y here? So we're going to choose 2 points. One of them can be the one right here, because we know based on definition of the tangent, that point is touching the line. So in this case, we know that the x value of this is 1. And the y value is 2. So 1 and 2. And we're going to choose another point. We're going to try to find a point on the line. We're not going to try to use a point which is very close to it. We're going to try to get as far as we can. And I can see that, let's say that this point over here is approximately on 10 and -4. And again, it is an approximation, so but this point is very close to 10 and -4. So I'll use those 2 points. Again, the points you want to choose, you gotta try to choose points that are far away from each other. And delta y, -4 minus 2, and delta x, 10 minus 1. So I'm getting that from -4 minus 2, 10 minus 1. And I end up getting to 2 significant figures. I believe I said that all numbers are good to 2 significant figures, so I'm going to round my final answer to -0.67. And my unit for the y, or the delta y, is meters, and my unit for the x is seconds. So it will be meters per second, and you can also represent this as meters per second, like this. Now for the second line, so I should be more clear here. I will say at 1 second, and I do need to leave a space between my time and my units. I'm going to do that just to make sure I'm modeling this well for you folks. So this is 1 second. And now for the second part, I'm doing it for 10 seconds. So for 10 seconds, the slope, assuming that this is already written there, the slope is going to be equal to the change in y over change in x. The change in y, choose any 2 points. This one over here, negative, this is 10, -2. This is 0, -2. So you can go ahead and say -2 minus 2 over 10, sorry, -2 minus -2, 10 minus 0. This is going to equal to 0. And my unit is meters per second. You don't need to display 0 as two significant figures in this case. It's just saying 0, it means it's exactly 0. That's it for my second one. And for my last one at 13 seconds, my slope. So if it's a flat line, and if you're sure it's a flat line, I'm okay with you folks just saying the slope is equal to 0 meters per second, or 0 meters per second. If you really want to make sure that I understand what you're saying, you can say because the tangent is horizontal. Or you can just write since horizontal, and I'm okay with that as well. And that tells me that you know that the line is horizontal and therefore it will have a 0 slope. And that's your final answer here. So this is how you find instantaneous rate of change using a tangent or slope of a tangent, and you find the average rate of change between two variables using the slope between 2 points.